So the whole point of trying to understand the structure of the atom was to be able to explain, predict, and apply things that we know about the different elements to how they actually react in the real world. So chemical reactions, physical properties, and other things that makes elements similar to one another and different, which connects to their location on the periodic table. So we're going to look a lot at periodic trends, and this is something you'll definitely have to be able to explain on the AP test. That explanation requires not just a memorization of what increases or decreases or a property unique to a specific element, but understanding the cause for that trend. All of it comes down to attraction between particles, explanations of Coulomb's law. But when we're doing that, there's a few key terms that kind of help us when we're looking at an atom to think about or to understand why the attraction may be different based upon the Q value, the charge, or based upon the R value, which is distance. So even though I put them in this order, I kind of want to start with number 2. When we look at an atom, whether we're looking at a Bohr model like this, or we're going a little bit more detailed with the quantum mechanical model and electron configurations, we've got our nucleus in the middle. We have energy levels and sublevels holding electrons. And then we've got our outermost levels and sublevels, which hold the valence electrons. The valence electrons are the most important in terms of chemical and physical properties and reactions. So those are the ones that we care about the attraction to more than the others. One thing that can change that attraction is the idea of shielding and distance. So distance is pretty simple. As I go to a higher energy level, that energy level is on average farther from the nucleus. Shielding is the kind of application of that, or the idea is if I am farther away with more levels, there's stuff, or in this case, electrons in between. So those electrons block or use up some of the positive charge of the nucleus, but they also repel those further out electrons, pushing them a little bit further. So when we're describing shielding and distance, it's a fairly simple explanation to connect to the periodic table. Each row that we go down, we add another energy level that increases the distance and therefore increases the shielding. The result of shielding, or one of the main results of shielding, is a concept called the effective nuclear charge, or we could call it the net nuclear charge. And if you are writing about this, you would often abbreviate that as Z sub EFF, or ZEF, or effective Z. This is how many of those protons, or how much of that positive charge from the nucleus, hasn't been used up or shielded by our core electrons. So this is a great example both of shielding and of ZEF. Here we shield with energy levels 1 and 2, leaving only a certain amount of the positive charge, or the nuclear charge, for those outermost electrons, the ZEF. The nice thing about ZEF is for neutral atoms, it's also easy to predict on the periodic table. As we count left to right across the periodic table, it's just based upon how many valence electrons that it has, so 1 through 8. And we would be able to kind of prove that by drawing Bohr diagrams for each of the atoms that would support it. But as I go across a row, I'm adding more protons, but not necessarily adding more levels. So that means each proton actually increases the nuclear charge felt by those valence electrons. Each time I go down a column, I am adding more protons, but I have added an entire another level of electrons that do some shielding. So if I compared beryllium all the way down to radium, for example, radium has several times more, 20 times more protons, but all of those protons are blocked or shielded by the inner electrons. For our purposes, ZEF we think of often as whole numbers like this, where we just think about total shielding, total ZEF. But the reality is there are some subtle differences. So when we do this, the Bohr model is probably the best description, because we don't really think about an S sublevel shielding the P sublevel, because they are not necessarily always in between the nucleus and that outer level. So we keep it simple with whole numbers and connecting it to locations on the periodic table. And right there, those are the two main factors in Coulomb's law that are impacting our attraction: how much positive charge and how much distance. But when I have all of these electrons, and I very briefly mentioned that they do repel one another, when electrons are close to one another, they repel. And the closer they are, the more significant that repulsion comes. So when we are in the same orbital, often that repulsion can become great enough that we start to see some differences in patterns than what we might expect. The example we've already looked at is chromium being an exception when we're looking at electron configurations. We also looked at with PES, nitrogen and oxygen. So when you find something that goes against the pattern that we would expect from a change in effective nuclear charge and a change in shielding, we need to think about how the repulsions between the electrons is different. The most important thing with this is that we're not kind of falling back just upon those tricks and phrases that maybe we learned in a previous chemistry or science class. That things want to be full, or things want to gain and want to lose. Full or half full levels and sublevels aren't stable because we said that they are. They're stable because they're maximizing attractions, they're minimizing repulsions. The attractions are unusually strong compared to other things. So we don't want to be talking about, oh, it's stable or it's full, therefore we know this. We want to explain why that fullness is significant. Additionally, we want to step away from personifying our atoms. We don't want to talk about things wanting to gain or wanting to lose. We talk about the attractions and the energy change associated with those things. In the next video or two, you'll find me kind of catching myself as I say things want to gain or lose. It's fine to think about that, but that's never our explanation. Explanation is, how is Zeph playing in? How is shielding and distance playing in? And do the repulsions have a significant explanation or a significant part in the property itself?